Hello, my name is Ester van der Voet. I'm a lecturer at Leiden University and my area of expertise is industrial ecology. I'll talk to you about criticality assessment and more specifically about the supply risk part of it. I'll go through the different factors that determine supply risk and how these are incorporated in criticality assessment methods. I'll end with some observations on criticality assessment for materials from the urban mine. Criticality assessment is generally understood to be a type of risk analysis. Some unwanted event is specified and the risk is then determined as the probability of the unwanted event actually occurring, multiplied by the impact of that unwanted event in case it would indeed happen. In the case of critical materials, the unwanted event is defined as not having access to a resource. The probability of such an event is then defined as supply risk, and the impact is called economic importance or vulnerability to supply risk. The more important a resource is, the worse it is when access is restricted. So, here we talk about the supply risk, the probability that there will be problems with access to a resource. How to measure the probability that such a thing will actually happen? In criticality assessment, indicators are defined and used for this purpose. Before we go into that, let's first have a closer look at the issues that determine such a risk for any specific critical material. In the first place, there's the risk that access in a sheer physical sense is somehow restricted. That could have various reasons. There may be a low availability of the critical element in the Earth crust altogether. The element may be rare in a literal sense. Or the access to the site where the deposit is may be restricted. For example, because the area is residential or is a nature conservation area. Or the site may be located in risky areas, for example in conflict areas. Or of a slightly different nature, but also under this heading, there may be very few mines that produce the material in the world altogether. So if anything happens to one of those mines, supply may be disrupted. And of a completely different nature, if the possibilities for recycling of the material are good, this may alleviate supply risk to some extent. In the second place, there's a risk related to unstable prices that disrupt markets for the critical element. Unstable prices may be caused by a mismatch between supply and demand. Critical materials are often produced as co- or byproducts of other materials. That means that supply is not connected to demand, and there will be a situation of either oversupply, causing prices to drop, or undersupply, causing prices to rise. Sometimes, therefore, mining companies leave the byproduct material in the ore to avoid the risk of oversupply. A similar story can be told for recycling. If prices are high, recycling can become a profitable business. But making available a large quantity of materials via recycling can cause prices to drop, with the risk of a loss instead of a profit. Likewise, the demand for the material can be quite unpredictable, as new applications have the potential to multiply demand, but phasing out might cause it to crash. This can also be a reason for companies not to produce the material. A third reason contributing to supply risk is global economic optimization. There's a powerful incentive for production to move towards areas where production costs are low. This is often associated with low labor costs or with low investment costs due to less strict health and environment regulations. This is one of the main reasons for the reduction of the number of mines worldwide, or the concentration of production in one or a few countries. It isn't that these ores can be found only in those countries, but that cost of production would be incompetitively high in other locations. As long as the drive towards global economic efficiency remains so powerful as it is now, this is not likely to change, and we are facing a lock-in situation. These three factors, restricted access, unstable markets, and global optimization, are translated into indicators that are used to specify the supply risk of critical materials. There are different criticality methods which use different indicators for this. These differences may have to do with the actors involved. Both supply risk and economic importance are different for different actors, consumers, companies, countries, and for different functionalities, energy, mobility, communication, etc. So how do the different criticality methods treat supply risk? Which factors do they include? The European Union has developed a method for criticality assessment. The supply risk is measured by an equation including recyclability, substitutability, and geopolitical risk. Recyclability is measured by the actual end-of-life recycling input rate, the share of recycled materials in the total input. Substitutability is measured by the substitution index, an expert estimation about the existence of a substitute in the applications of a critical material. Geopolitical risk is measured by the Herfindahl-Hirschman index, an index that says something of the concentration of the production of the material. Several observations can be made. A first is the absence of any geological element in the supply risk equation. Apparently, the EU agrees with geologists that geological scarcity is not an issue for any commodity, at least for the present. Another interesting thing is that the economic element is missing. The equation includes only technical aspects besides the HHI. This may lead to the conclusion that economic and market aspects, always mentioned as extremely important, are considered of minor interest by the EU. And finally, it's interesting to see that substitutability is included in the equation. One might place this aspect rather under economic importance. If there are substitutes, the material may not be so crucial for our society. In fact, the SI is also a part of the economic importance axis, though defined a bit differently. Other criticality assessment methods include different aspects. So far, the whole field is still very much in development. There's one suggestion I would like to make, or at least one debate I would like to start. How about developing a separate criticality assessment for materials from secondary production? It would solve some problems with the present indicators. It would also acknowledge the importance of the urban mine and the fact that this urban mine is radically different from the geological mine in a number of aspects. Some risk factors may be the same, but others are really different. Some do not apply to secondary production, others only to secondary production. I will mention a few examples. Obviously, there is no problem with the regulatory restrictions or geological availability from the urban mine, and neither will conflict areas play a role. Most important, perhaps, is that the resource is available throughout the globe, very dispersed, instead of concentrated in a few mines. On the other hand, we are dealing with a mine that cannot be accessed just like that. Materials are in use and will only become available when discarded. This provides a different type of supply risk. The risk of supply shocks via large quantities becoming available is absolutely present. However, it does seem likely that production from the urban mine can be regulated better to the demand than that from by-produced primary production. Because the urban mine is everywhere, there will be many more actors in the significant secondary production sector. Local cooperations and specializations may develop, leading to a much more diverse and dispersed type of production with less risk of collapse. Technologically, there are some challenges to produce from the urban mine. Setting up a good collection system is a challenge for the urban mine. Mining and refining may face difficulties of a technical nature. This has to do with the quality of the material from the urban mine. For example, low concentration applications that are difficult to recover or lead to accumulations of impurities. On the other hand, there is much more that we can actually do to make the material available. Much more than in the case of the geological mines. Geological stocks are what they are, but the urban mine can be made more accessible by a different design of materials, of products, of buildings, infrastructure. All in all, it seems to me that there is much more to the urban mine than can be captured in a simple end-of-life recycling rate indicator. In one way or another, that must be acknowledged in criticality assessments.